So as a background of our experiment, we used the exact same experimental setup one team from Florida in the 1990s used to detect the speed of light. Now you can measure this using many different ways, but what they did is they used barium fluoride detectors just like we did. The scientists are Lee Chow, Stephen Lukic, and Ken Hopkins, and they all teach at these respective universities and positions. And so our photon source was sodium-22, which decays by beta positive radiation. We had a picture here, but it didn't show up. So it emits a positron, which reacts with electrons in your source holder, just like the atoms of the gases floating around in there. And when the positron and the electron interact, they annihilate. So they release 2 photons, and they go off in separate directions, and each of them hits one of our detectors, barium fluoride detectors. And they measure when the photons hit them, and they actually measure the time delay between hitting the first one and the second one. So yeah, that's a picture. Yeah, so you can see here that you have your carbon-10 isotope, then by beta positive decay it releases this positron, and one of the protons turns into both a neutron and positron and a neutrino. So our objective was to determine the speed of light using photon emission from the annihilation of matter and antimatter. So yeah, this is just one of the ways you can use to measure this, because the photons, which are light particles, by measuring the speed of those, you could technically determine the speed of light in our room.
Alright, so this is our equipment. So this, we had a sodium-22 source inside this lead chamber, because otherwise the radiation, since it was one of those powerful sources, would get on us, but not very safe. And then this is our gamma detector, which determined the photons, when they hit. And this is what is hooked up to the computer. This is the voltage supply, and then this is the constant fraction disk, or the CFD. This is the time calibrator, so I'll explain more of that later. And then this is the delay amplifier, so it allows you to determine the relationship in the channels in time. And this is the time to amplitude converter, and this is also the multi-channel analyzer. This is our setup. So over here we have what was the right picture, and it was hooked up to the computer. And those were the 2 detectors and the photon source. So yeah, he had explained how the photons shoot out. One will go that way, and one will go that way, and they'll each hit the source, the detectors.
Okay, so the basic procedure we did was first we began with the setup as we went over before. So then what we have to do is we have to calibrate the time, because the computer program we use, it registered things in channels, which aren't really a very useful unit. So we had to convert it into something more useful. We used nanoseconds. So what we would do is we had a dial, so it would shoot out a photon every 0.2 nanoseconds, I believe. And then we would measure how many channels it recorded that as, and then we could use that, use a slope graph to convert that into channels. So then how the thing worked was you would launch 2 photons, and then it would measure the time difference in between them hitting. So we did that. So we measured that for various positions. So we'd move it increments of 20 centimeters and then record the time difference from the various positions. And then we used all of this data to calculate the speed of light.
Okay, so our results came in a graph that looked like this, which basically counted, this is the number of photons that were collected at certain channels, which, like Henry mentioned, aren't actually a standard unit, but instead are just proportional to the time that it took the photons to travel to the detector. So each of these peaks is actually the number of photons at each channel for each different distance that we put the source from the detectors. So this took a couple trials to do, and as he said, the distance, the change was 20 centimeters each time, so this is the change in channels. So we had to determine next, and this is a table where we recorded the mean channel for each peak and the distance, the position of the source that we put it at for that channel. So the next thing we had to do was calculate what exactly the relationship was between channels and time so that we can get a numerical value for the channels that we got.
Alright, so this is the map. To determine the relationship between time and channels, we changed the input to generate a pulse every 0.01 microseconds. So then we took the pulses and we're able to determine how many like microseconds were in the channel, so we're able to convert that data into like seconds. And then looking at the difference in channels between our known time interval, we're able to determine the relationship to be 812 channels for every 0.01 microseconds. This is our like equation that we use. So we have a channel over time, which was like our fraction, so like it was our graph and data and stuff for like this kind of stuff. And then we have our change in distance over our change in channel. And we had to multiply that by 2 because we moved it 20 centimeters closer to one source and 20 centimeters away from another source. So it's a total change of 40 centimeters. So we had our data, we had to multiply that by 2. So then eventually the channels both, they cancel out. So we have distance over time, which is equal to velocity, which gives us the speed of light.
So we did this for a couple of different of our different trials because this is changing channel, and we took the values from different distances. So we had a bunch of channels to do. So we did each trial is the change between two of the trials that we did. So 2 of the different channels, and we used that to calculate the speed of light. And so our calculated average was 2.9 times 10 to the 8th meters per second, which is pretty close to the accepted value of 3.0 times 10 to the 8th meters per second. And so our data was pretty close, but our error is, the error does exist. So
Yeah, so the error was only 7 million meters per second. It might seem like a significant amount, but when you're dealing with the speed of light, you have to remember is 300 million meters per second, so that was only a 2.33% error, which is not that bad. So then some of the sources of that was the two detectors we used. One of them was basically a start switch for the timer, and the other one was a stop switch. So what would happen sometimes if it was positioned incorrectly, it would reach the stop switch first and not do anything. So then the photon would hit the start switch, but then the thing it would be timing would be basically meaningless because it would be, instead of timing the difference in when they hit, it would be timing the interval between the release of the photons, which is not very useful information. Then they're traveling through a medium air, so light, it isn't the exact speed of light because light will still get the exact 3.0 times 10 to the 8th meters per second is the speed of light in a vacuum. So in a medium, it will be slowed down. And finally, there was also a chance for human error because if we were moving the photon emitter back and forth, we were measuring how many centimeters it would move, but we might have even a difference of a couple micrometers when you're dealing with time so small and velocities so large that could make a substantial difference in the results you obtain.
So yeah, so now we have.
Oh wait, no, you have to go to the end.
Not yet.
Oh yeah.
Okay, so now we have a little surprise. We decided to summarize everything we did in a rap for you.
Yeah.
It's gonna be good.
I said, what is the speed of light? The light in air and it don't stop a rock to the pen boogie say open up your brain to the rhythm of the rhyme so sweet. Now what you hear is not a test, I'm rapping to the beat. And me, the data, and my friends are gonna try to give you the treat. See, I am the next Newton, and I'd like to say hello to the moms, to the dads, to the teachers and the kids, the young and the old. But first I gotta show you exactly what we did. To find the speed of light to the best of our might, let's rock. We won't stop, the lab that'll make your body rock. Well, so far you've heard my voice, but I've got to move along. And next she'll explain the experiment. Come on, yo, sing that song.
Check it out, I'm the beta, DK, the source is NA, and the rest is FOY. You see, I end up in the release of a photon. These reasons I'll tell you why. The mass is 511 of the positron and the electron. You see, we got the same mass but different charge, and we explode their middle bond. My body's ground, I got 2 photons that definitely ain't the whack. I got 2 gamma detectors and a scintillation
talking about calibrate, amplify, energy that seemed to never end. But I wouldn't miss a second or a minute, I reckon, not a minute till I've done it again. Everybody go, proton, photon, what's it gonna be today? Get a fly graph, gonna get some data and come out with a definite speed. Everybody go, proton, photon, speed of light. Say, if you want the speed of light, we bring it straight out of South Bend.
Word.
How do we get that up? Just click through it. Okay, there's a point to this slide because they had showed us a video on what not to do on PowerPoint, and they had decided to put a really bright end green screen with those like really bold obnoxious letters, and I decided to flip it upside down because you know some people will go like,
Is anybody here colorblind?
yeah.
If you're
Because if you're red green colorblind, it's just a green screen or brown screen or whatever it is. It's
Okay, thank you.